Let's now consider aliasing, or in other words, how it is that we choose our matrix of integers CAPN. Now, just the key points to recall from above. Our basic basis function is a complex exponential, as I'm showing to you here, where at each particular sample point, it would have the standard formula value. The sample points themselves are constructed as follows from an M matrix, where M has the standard counting, 0, counting all the way through to the end of the row before we flip over our odometer, so to speak. S is the size matrix, and R is our lattice constant matrix. Now, the best way really to understand what is going on in this aliasing and why we have this particular choice of form for the integers n is to take a simple example. So let's consider a very simple example. And in this example, which we will explore in full detail, we will work in d equals 1 dimension. And I think you will see, once you understand 1 dimension, it'll be quite clear in your head what happens in 3 dimensions. 3 dimensions turns out just to be a simple sort of tensor outer product of what's going on in each of the individual dimensions. So we'll look at d equals 1 dimension. And the size then, instead of having 3 different sizes, because I'm in 1 dimension, there's only one size for me to talk about. And we will look at a case where that size, s, equals 8. Very good. So now let's try to draw our space and try to understand how each of these objects behave in this particular case. So for my space, it's just a one-dimensional space. It lives along a line. So let me draw a nice, generous line here, something like so. And my line will then, my unit cell on my line goes from 0, and it extends all the way out to point R. Now remember, there's only one lattice vector here, and it's not even a vector, it's just a scalar value because I'm in 1 dimension. So the length of this periodic interval then is R. The other thing you'll notice is I'm using a notation from real analysis where the square bracket indicates I'm including actually the point at 0 in my primitive cell, but I am not including the point at R. The reason for that is that the point of R actually, mathematically, is equivalent by periodic boundary conditions to the point at 0. It really is a redundant extra point, if you will. It's just an image of the original point, and I correspondingly draw it then as a dashed circle instead. Now, if I think about the sample points that I'm dealing with, that would be my formula here for R. On the sample points, then, R will equal a set of integers, m. Remember now that this M matrix now doesn't have 3 columns, but 1 column because I'm in 1 dimension, and the value of a generic point along the column will just be some integer between 0 and s minus 1. So I will index those by just lowercase m. That will be that m value. The size is 8. I'll just write down the generic formula. So it's m over s in this case times r. The R matrix, again, is just a 1-by-1 matrix now of size R. And so in this case, it will be, again, m over 8 times R. So let's see what points we have then. You can see I will have when m equals 0. Oh, right? Remember, m equals 0 up to s minus 1. So it goes from 0 to 7. So my first point will be at 0R, will be the point that I've drawn for you here. The next point will be at 1/8 R, 2/8 R, and so forth until I reach 7/8 R, and that's where I quit. So this will be divided into equal eighths. As a diagram, it's easier simply to divide my line first in half, and then in quarters, and then in eighths. And you can see then the various points. This point here, the first point corresponds actually to m equals 0. The next point is m equals 1, m equals 2, so forth, all the way up to m equals 7/8 of the way. And then finally, 8/8 is not included because that is simply an image of the point at 0. All right, good. So those are my points R. Let's now consider our different possible G vectors. So G follows the formula that we are seeing here. So g then will equal 2 pi in general times an integer n. N now, notice, is just going to be a single column of integers, 0, 1, 2, counting in that way that we're trying to understand. But the generic integer value I will just call n. And of course, then, I have to include a factor of the inverse of my lattice matrix. My lattice matrix is one vector that has one component. It's just r, right? So the inverse of it would be r, like so. Now, to get an idea of what these different basis functions look like, it's very helpful, actually, to begin by considering the basis functions themselves at each of my sample points. So if I were to compute this B alpha at RP, actually, I don't want to cramp myself up here. I have to find an appropriate location for doing this mathematics. Where do I want to put it here? Maybe I'll squeeze it over here. So if I want to put B alpha at RP, that should equal e to the I g dot r. So it'll be e to the I 2 pi n over cap r. That is g from the formula here. And then RP, my sample points, follow this formula, m over the size s times r. And the nice and interesting thing you'll notice is that the lattice constant cancels out. So I simply have some interesting combination of integers as I construct my basis functions. I get complex exponents of the form 2 pi I, the product of my two integers, n and m, divided by my size s. My size s actually here is 8. So this is the form that I'm looking at. So if I look at my first basis function, which corresponds to the first g vector, the n equals 0 basis function, what I find is when n equals 0, my basis function always gives me e to the power 0. I just get the number 1, always. No matter what the value of n is being multiplied by n, I simply get e to the 0. So I have a different complex number that lives on the unit circle, because these are complex exponentials. It lives on the unit circle, and they all have the value 1. So I'm going to make a convention that I will draw these complex exponentials as arrows, as you normally would in the complex plane. But the base of the arrow I'm going to put at the point corresponding to where I'm evaluating my basis function. So for the first point, I get 1. So that vector points just on the real axis. My second point, I also get 1. So the basis functions look like this. The basis function has these values that have this general complex exponential appearance, which is just simple constant all the way at all the points. And even, it stays constant, of course, here, even when I get to m equals 7. And if I were to go to equals m equals 8, it would also be the same thing. I will draw that with a dashed line, notice, because this is just an image of the first one. And very nicely, of course, I'm fitting periodic boundary conditions. What I expect to see at this last point is indeed what I find at the first point. Very good. So that example might have been somewhat boring, right? It just looks like a constant function over here. I see no change in my function. And indeed, that the natural way to interpret this is that I have a plane wave where the wave vector is just 0 because I'm getting the constant 1. So in this case, when n equals 0, what I end up with is something that where g equals 0. And this very nicely follows my standard mathematical formula. I'm expecting 2 pi over r times the corresponding integer n for my wave vector, and in fact, that's what I get. Somewhat of a trivial case, but I think we understand that one. Now let's see what happens when I go to the next case. Let's look at n equals 1. For the n equals 1 case, right, I have to draw again my space. Looks like so. And it helps to put the first point and then divide in half, and divide in half again, and then again to get my eighths. Here now things are going to be a little more interesting. In this case, n equals 1, and because n equals 1, my complex exponential then will be 2 pi over 8 I times m. So that's pi I over 4 times m. So in this case, I know I'm getting a little cramped, but this will be I pi over 4 times m. So now when m equals 0, which is my first point, of course I just get 1 for that exponential, so my vector would look like so. When m equals 1, I now have a point on the unit circle with a phase angle of pi on 4, which would be 45 degrees. So my next one I would draw like so. When m equals 2, I now have twice the angle. I have pi over 2, which would be 90 degrees. The next one would be 3 pi over 4, which just means I have another pi over 4 turn off of the one that I had before. So I think you can see what's happening is I'm turning 45 degrees, or 1/8 of a circle at each point. And what's very nice is by the time I get to the final image point, whoop, I didn't draw that one right, I anticipated. By the time I get to my final image point, I have indeed rotated exactly back to what I would expect for perfect periodic boundary conditions. Very nice. Now, in terms of the reciprocal lattice vector associated with this, or the wave vector, I should say, when I look at the complex exponential behavior that I'm seeing, definitely I'm seeing complex exponents, so this definitely looks like wave-like behavior. It has an interesting periodicity. Here I can sketch it for you. Exactly one period fits in the distance r. So the wave vector associated with this should be 2 pi over lambda, but lambda is r. And this again fits my expectation from the formula, because what I have here is 2 pi over r times an integer, namely the integer 1. So when n equals 1, my formula for g gives me just what it is that I would expect. Very good. We'll try one more example here in the progression, and then we'll kind of skip ahead to where things get extra interesting. So if I go now to n equals 2, say, I think you will getting the idea here what's happening. Here's my halves, quarters, eighths. Now, n equals 2. When I insert n equals 2, I have 4 pi on 8, or pi over 2. So the exponentials I'm looking at are e to the I pi on 2 times m, which means I'm simply turning 90 degrees, or pi on 2, at each step. So when m equals 0, of course I get 1. Then I turn 90 degrees, another 90 degrees back, down, forward, up, back, down, and perfectly periodically forward again. This is good. Associated with this, I can see that I've got one full wave here and a second full wave here. So the wave vector is 2 pi over lambda. Lambda is now r over 2 because I have two different waves. This, of course, is 2 pi over r times 2, and again fits the g equals 2 pi times my integer n times the inverse of r. Perfect. Now, I think you get the feel what happens then if I went to n equals 3 and so forth. Now, let's anticipate and go to the a little bit of a more extreme case that makes things a bit more interesting. Let's try the last one in the row, n equals 7. What happens if I simply keep increasing n? So here's my image point, my initial point, halves, quarters, eighths. Now so this is going to be n equals 7. Now the exponential that's involved is e to the I. I have 7/8 times 2 pi, right? Or 7 pi on 4. 7 pi over 4 times m. That's what I'm expecting. So when m equals 0, of course, I have 1. E to the 0 is 1, so I have no angle. Now, when m equals 1, I have 7 pi on 4. Now, 8 pi on 4 would be 2 pi. So I'm just 1/4 short of 2 pi, so I actually am pointing downwards like this. Like so. When m equals 2, I have 7 pi over 2, right? So 8 pi on 2 would be a full circle, so I'm pi over 2 short of a full circle. That means I'm pointing straight down. And you can continue evaluating in this way, but I think you can see the pattern of what's happening. There are two ways of looking at this. I could think of myself as each time circling around a full circle minus pi over 4. So that's how I get to here on my first try. And then here you could think I've turned a full circle except for pi over 4, and that's how I end up straight down. Alternately, clearly I could think of this as having turned a negative pi over 4 on the first step and another negative pi over 4 on the second step. So you can either think of it as going all the way around except for a quarter, or just as going 1/4 backwards. So let's do the 1/4 backwards. That's easier to picture. So here I'm 1/4 down, 2/4 down, right, which would be pi over 2. I can turn another, the same amount, but backwards, like so, straight up, up at 45. And very nicely, again, when I get to the last point, perfect periodic boundary conditions. Now, when we look at this, you will notice that the period that's involved is, in fact, one full wave in lattice vector r. So I would tend to call this g equals 2 pi over r, 2 pi on lambda. But because the phase now appears to be progressing in the backward direction rather than the forward direction, we naturally associate this with a negative wave vector. And this now, I think you can see, really would fit our pattern much better if we call this 2 pi on r times minus 1. So that is what is, in essence, happening. Why we choose minus 1 as the last integer n. Because when we see behavior like this in our basis function, and we inquire as to what is the natural wave vector associated with it, we see, well, we really have two choices. We could think that between our grid points, things are changing so quickly that I have almost a full circle each time. But much more naturally, if we had a good sampling of our functions, a good density of points, we would think, well, our function shouldn't be changing too quickly between points. So it's much more natural to associate the backward progressing wave vector, the equivalent negative wave vector, with that corresponding behavior on my grid. Very good. So that's the essence of the idea. Let's just clear up a little bit of the mathematics, and then we'll summarize our principle here. So let's try n equals 6. So for n equals 6, this will be e to the I. Okay, so I'll have 6 times 2 is 12 pi on 8, right? Which would be 3 pi on 2. 3 pi on 2 times m. And then here we can make my space with my repeated point, my 0 point, my half, my quarter, my eighths. And now the first point is always 0, of course. Is 1, 0 phase. The next point will be 3 pi over 2, right, which is just pi over 2 short of full 4 pi, so it's pointing straight down. And again, our two choices are either 3/4 of a circle this way, or you can view it as 1/4 of the circle backwards. I prefer that direction, that view. So then the next one will be another quarter backwards. It'll be straight back, up, forward, down, back, up, and forward for my periodic boundary conditions. The wave that I'm representing then goes down, up, right, down, up. The reciprocal lattice vector then, or the wave vector, is 2 pi over, there are 2 periods in one of my units, so it's r over 2. I see the phase progressing in the negative direction, so it's associated with a negative value, which gives me 2 pi over r from the standard formula times the integer minus 2. So, at the very end of the row, I use integer minus 1. Right before that, I use integer minus 2, integer minus 3, as you can see. And I can progress in that direction. And at some point, we're going to meet in the middle. And the middle point, the interesting point here, is going to be n equals 4. And this is worth looking at. There's some discussion that's worth having here. It's a very famous point, actually, in the theory of spectral methods. There's my center, my end, my quarters here, and my eighths. When n equals 4, when I look at my general formula, it's 8 pi over 8. So that's just going to be e to the I pi m. Interesting. So when m equals 0, it's 1. When m equals 1, e to the pi I is minus 1. So I'm pointing backwards. And then so I'm just flipping sign. Forward, backwards. It's a little hard to draw. Forward, backwards. Forward again for my image point. Perfect periodic boundary conditions. And you can see now I have to make some kind of a decision because I'm either traveling half a circle in the forward direction or half a circle in the backward direction. It is very hard to decide which of these two it is. So at that point, G will have a value of 2 pi over r times 4, but it's a matter, integer 4, but it's a matter of us trying to decide should this have been plus or minus. And in the convention we just decided to use for our course, it turns out, for reasons we'll see in a moment, it really shouldn't matter much what we pick for this particular point. We actually happen to choose plus. Now this frequency where your function is flipping signs between your grid points, where you can no longer rationally decide which is the least amount of phase change, whether it's a positive or negative traveling wave. There's a special name for this frequency. This is called the Nyquist frequency, and it comes up very frequently in the theory of Fourier analysis and sort of the ultimate limits of resolution. So let me just write that down, Nyquist frequency. Very good. So I think now we have a pretty good understanding of what's going on. I just like to summarize this behavior in a principle, which I like to call the sufficient sampling hypothesis. And this finally explains how we choose that particular form for n, sufficient sampling hypothesis. The point is to, this is the construction of n. And the logic goes as follows. Assuming we have sufficient grid points S, right? I mean, when we do a calculation, I expect that we're going to be responsible about it. And we're going to put down a sufficiently large number of grid points that we can resolve the problem. So assuming we have sufficient grid points S, the physical fields, like the density, right, or the electrostatic potential, or the wave functions, change slowly between grid points. And so we choose the consistent value for our wave vector G, right? Because we had two choices, a plus value or a minus value. We choose whatever is consistent with the actual behavior of the basis function with the least magnitude of the corresponding wave vector, right? We don't choose the positive one if it's larger. We choose the negative going progression for our wave. Now, how can we know if a given calculation satisfies the sampling hypothesis? Well, and of course, this prescription that I just gave you gives us our rule for n, that n should start at 0, 1, count all the way up to s over 2. Then at the end, it goes from -1, -2, and counts down until we get to And if you count out the total number of points, it turns out to be this value is minus s over 2 plus 1. And really recall, this is the one where we just arbitrarily chose the positive value on s over 2. Now, how do we know? To verify this, there's only really one way to know if you've properly sampled your system. You simply increase s and verify that there are little change in the final result. Now, to wrap up, I just want to discuss a claim I made a moment ago. I had claimed that, indeed, it shouldn't matter much what choice we make here for the sign of the wave vector at the Nyquist frequency. And my argument for this is as follows. If you have a field, a density, or an electrostatic potential in your calculation that has a significant amount of Fourier component, where the sign of that wave is flipping sign between grid points. If that's true, you clearly do not have sufficient sampling. Right? There should be very little Fourier amplitude at a frequency like this, where your function could possibly be flipping signs between the grid points. That is not smooth behavior. And so if you were to increase the number of grid points in such a calculation, you would see significant changes as you increased that sampling size, until the changes with increasing sampling become small, at which point you should have very little amplitude actually extant on the Nyquist frequency. And so then correspondingly, whether we choose one wave vector for it or the other, because there's very little amplitude at that point, then that particular choice should not affect your results in the end. So that discusses that finishes our discussion of the sampling hypothesis and really of spectral methods. If you can understand this one last subtlety and everything we've said previously, you've got a very good handle on how to use these methods for solving differential equations.